All right, let's go ahead and start doing stuff. So if you're here, how many of you are here and trying to add the class still? Show of hands. Keep your hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, good news. So here's the deal. I went to the registrar and I tried to get a bigger classroom for us so that I could let more people into the class. And the registrar, they were polite enough not to laugh at me directly, but they essentially said no. There's no way we can get another classroom unless we move this class until like 4:30 in the afternoon. How many of y'all would like to move the class to 4:30 in the afternoon? Me either. I want to go home. So that was not pretty much an option. But we were able to hire another TA. So the TA is really the limit on the class, and I can expand this class to no more than 45 because there are 45 seats in here. So if you're on the wait list and you're trying to get in, email me today's code word, which is actually a code phrase, chicken pot pie. Send me an email that contains the words chicken pot pie, and you will maintain your place on the wait list, and I will be letting about 10 more people into the class. So that's good news, right? Yeah, all right. So let's go ahead and get started for real now. Hi, everybody. How are you all doing today? It's a rainy, yucky day, but let me tell you, I'm glad that you are here today, because today is a very big and important day for a couple of reasons. Big day. First, it is my son Alex's 3rd birthday. Yay! Yay, Alex. He's a cutie. He's been very excited today, going and telling everybody it's his birthday and getting hugs. That doesn't really matter to you all. It's important to me. But the thing that's important to you is that today is the single most important day of class for the entire semester. Today, I'm going to tell you the one weird secret, the one shocking thing that you don't know about computer science and about programming. There is one important thing that you have to know to be successful in this class and be successful in programming. Today I'm going to teach you the secret of programming success. Are you excited? This is the one thing that if you remember, you take from this class, I want you to remember forever. If I run into you 10 years from now someplace and I say, what is the one thing you remember from this class? Other than me being a raving lunatic, the one factual knowledge piece, I want you to remember this one thing, okay? This one thing, and here it is. Oh, wait, but before we get started, sorry about this. It's my son's birthday. I have to get a birthday cake for him, and we ordered a strawberry cake from Patisserie Poupon on Wisconsin Avenue, but I'm not really sure where Wisconsin Avenue is. Can anybody tell me how to get to Wisconsin Avenue? No? Yeah, how do I get to Wisconsin Avenue? Okay, let me just write this east. Walk up the main gate and walk parallel to M Street. Parallel to M Street. Okay, so walk east. Is that right? Yeah, walk east from the main gates. Go through main gates. Which way is east? Parallel to M Street. That way? That way is east. So I'm just going to go that way. I'll go out the main gates. I'll walk a while, and then what? And then what do I do when I reach the bunch of shops? Okay. So I could be able to use Google Maps. So essentially what you're doing is I have to go up here. I go like out the front of the building. I find the main gates. I just go straight out the main gates and I get to Wisconsin Avenue. Anybody can tell me where Patisserie Poupon is from there? Left. And then where do I find it? Okay. So from here, I go out the building, walk east, and I'll get there, and I can get my son's birthday cake, and he will be happy, and I'll be happy too, because it's a really awesome cake. Anyway, thank you. I'm sorry for the interruption in the lecture. Let's see where we were. All right. So I was about to tell you, what was I about to tell you? The one thing that you need to know from this class, and here it is. Anyway, you're saying, what the hell are you doing, Clay? You had this giant build-up. You were going to teach us one thing that was super important, and then you interrupted yourself to do something that was I could have just done on Google Maps because it's stupid, right? So here's the deal. What I did is actually related to this class in that what we have just done is essentially the one thing we're going to be spending most of the semester doing. What we did is we developed for me step-by-step directions for me to get from here to Patisserie Poupon on Wisconsin Avenue. Okay? Step-by-step directions for me to get to here to Wisconsin Avenue. What relation does this have to programming? Anybody programmed before? I know there's a few of you. Don't be shy. Now that I know it's you, I'm going to pick on you all semester. What's your name? Matt? Okay, what does this have to do with programming? Yeah, absolutely. Programming is just developing step-by-step instructions for the computer. And what is this called? An algorithm. An algorithm. All the computer is a tool, an instrument, a machine that can execute an algorithm. An algorithm. We're going to hear this word a lot, algorithm. Let's give it a real definition. Sorry, in just a second. So what I'm saying is that every computer program that you're going to write throughout the semester is just an expression of an algorithm. When you write a paper, what is a paper? It's an expression of an idea. It's an argument about an idea. When you write a program, it is an expression of an algorithm. Even though this class covers programming, what we're really interested in is the thought process on how to develop these algorithms and how to think about how the computer works and how we can develop algorithms that work in the way the computer works. Every computer program is just an expression of an algorithm. And when I say just an expression of algorithm, that just hides a lot of the complexity of what we're going to be doing. Because this part, the developing of the algorithm, is really what the class is about. The language is just a way for us to express what we have thought about, just like writing a paper is just a way for you to express ideas. All right? So what we're going to focus on is this developing algorithms. You will not be able to write a computer program without understanding your algorithm first. And let me just tell you, if you sit down and you just start writing stuff without thinking about your algorithm, you're going to have a bad day, okay? I should have made one of those little meme pictures of the ski instructor saying, if you don't have your algorithm, you're going to have a bad day. And the reason is because the program is just what you're trying to do. And if you're doing the program and the algorithm at the same time, you're probably not going to be that happy, okay? As you get along and you program more, you can get away with this. And I kind of do this a lot when I program. And here's what happens is later in my program, I find out that I made some horrible mistake that I didn't think about early on, and that would have been better if I'd thought about it. All right, let me reinforce this some more if I haven't enough, because this is super important and is the thing that gets the one shocking secret. I'm going to teach this class like BuzzFeed, right? The one shocking secret, the thing you need to know, one thing they won't tell you is that you need to have an algorithm before you write your program. It's important. So, an algorithm is an ordered series of steps used to perform some task. And the example we did when I interrupted you was the algorithm to get me from physically standing here to walking over to Wisconsin Avenue to pick up a cake. All right? That was the algorithm we talked about. A program is an algorithm that is expressed in the form a computer can execute and humans can understand. An algorithm is a program. A program is an algorithm expressed in the form a computer can execute and humans can understand. Both of these things are important. Both of these things are very important. So let's take a look at each of these individually. First, the form a computer can execute, and next, the part humans can understand. When you specify an algorithm, you must specify the algorithm in terms of whatever entity is performing it can do. So for example, we had an algorithm for me to walk from here over to Wisconsin Avenue, right? You did not say teleport over there. You did not say fly. I am sadly incapable of those things. That would be pretty cool if I had that and knives that came out of my hands. But you must specify the algorithm in terms of what the entity performing it can follow. So for example, say you gave me directions, right? If you wanted to give Superman directions to Patisserie Poupon saying, Superman, there is a sale on strawberry cakes. You've got to get there fast, right? Superman wouldn't be like, all right, I'll just go through the gate. Superman would just blast straight up through like all the floors above us, leave a big hole in the roof, shoot up about 800 feet in the air, look for Patisserie Poupon with his X-ray vision, and go straight there, right? None of this Google Maps stuff, none of this walking stuff. He would just go there. If we had Batman, we might give him different directions as well. That'd be more like directions for me, right? Does that make sense? So when you're working on your algorithm, the algorithm that you specify has to take into account whoever or whatever is executing it. Now, we're going to spend some time talking about this, and this is going to be counterintuitive to you, but computers are really very incredibly limited in what they can do. If you look at the hardware of a computer, it cannot do very much. I'm going to go into this a little bit today and more next class as well. We'll talk about what we can actually make the computer do. It can't do much. How many of y'all believe me it can't do much? How many of you have used computers and think I'm insane? How many of you just think I'm insane? Okay, yeah. The other part of a program is that it is an algorithm expressed in a way a computer can execute and people can understand. All right? People can understand. This is super important. The reason for this is that programs and programming is really a team sport. Just like writing a paper is a way for you to express your ideas to people, programming is a way to get the computer to do something, but it's also a way that when people look at your code and your program, they understand what you're doing. Now, programming is team sport, and out in quote-unquote the real world, you will not be programming by yourself very much, unless you're an eccentric, reclusive genius, right? Or an eccentric, reclusive, not genius, loser person, perhaps. But programming is a team sport. If you end up in a position where you're programming, and this course doesn't require you to do that, you can apply your skills in many ways, but if you end up in a position where you're programming, it will be a team sport. There will be ones or tens or hundreds or possibly thousands of other people working on the same code that you are working on at the same time. How many of y'all think for something like Mac OS, there's just like one guy sitting around writing it? Or Microsoft Windows, or anything like that? Minecraft, there's literally just one guy sitting around writing it, but he's like the genius guy. Most of the time, there's big teams who do things. Now, in this class and many others in the curriculum, if you keep going, programming will not be a team sport. And the reason is that it's not a team sport in the real world. It's that you need to develop your individual skills individually before you're able to participate in a team. Say that we took a bunch of you and split you up into groups and we're trying to teach you Australian rules football. Anybody know how to play Australian rules football? All right, so I would want you on my team because the rules are crazy, right? But what ends up happening is if you have teams where some people have better skills than others, the people who already have the skills tend to take on most of the work, right? And so if you show up on a team and you're going to be a programmer and you have weak skills, people will be like, yeah, you can go get us bagels or something. Right? So we want to develop your individual skills individually before we start doing things as a team. Does that make sense? Which is why when I talk about all the honor stuff, you're not to look at each other's code. All right? But don't think this is the way it is, that sitting in your room in front of a computer programming by yourself is computer science, because it's not. It's actually very team-oriented, and there's a lot of stuff that goes on. It is important for you to make your code clear to humans, even if it means that it is not optimal for the computer. How many people have programmed before? Just a few? I know Matt did. What's your name? Alan, what did you program in before? Java? Someone else over there wave? Java? What are you programming in, Matt? Python? Okay. So those are languages where performance is not optimized over things, so I don't have this, but there are some people who come into the class and they have written a lot of programs, and I'm glad that there's no one here because there's no bad habits to break. Where people come into the class and you show them a way to do it and they go, oh, that's slow, we could make it a lot faster if we did this. But the this that they do makes their code a lot harder to understand. In this class, we want to make our programs clear. We want to make it easy for people to understand what we're doing, and it doesn't matter if it's slow. Performance doesn't count, okay? Performance does not count. As long as your program runs through and finishes in some reasonable amount of time, that's fine. We're not going to be timing you and racing your code. If you're interested in that, what ends up happening is after you've written your code, You can make your code run faster. The thing that dominates in how long a program takes to run is not the way the code is written, but the algorithm that it implements. And later in computer science, a couple of classes on, you get into a course that is named algorithms, shockingly. And in algorithms, you study algorithms and how your choice of how to solve a problem influences how long it takes. Okay? So we're not going to worry about how fast it is. We can worry about it later. The other thing is you may not even need to optimize your code at all. Computers get faster all the time, and computers are pretty dang fast now, as we'll see, so you may not even need to optimize it. All right, so to go back, where we came from, important concepts, things that I will count on you knowing from now until the end of eternity. Okay? If I encounter you in the afterlife somewhere and ask you, I will expect you to know this. A program is just an expression of an algorithm. Everybody say that? To write a program, you must know what algorithm you're trying to express. Right now, you don't have to repeat after me for that. You will in a second. Right now, you have to think about your algorithm before you write your program. We're going to make this easy for you. I told you there are going to be 5 programming projects. For the first 2, I'm going to make you write your algorithm in a different form before you write your program and turn it in, to make you think about it. What's going to happen on the 3rd project is I'm not going to make you do that. And then what's going to happen is you're not going to do it, and then your program's going to have all sorts of problems, and you're going to be sad. And I'm going to stand up here, and I get to say, I told you so. Actually, it won't be here, because some of you do it. It'll be in my office hours. You'll show up and be like, I didn't get started. I don't know my algorithm. I'll be like, remember the first day when I told you so? All right. So I'm going to make you do the algorithm for a couple of programs, but not all of them. And then later, you're going to be on your own, but I still absolutely positively recommend writing down the algorithm before you get started. Okay. Now, I mentioned earlier that computers are super limited in what they can do. Does everybody believe me? Yeah? All right. Let's talk about how limited they are. At least what computers can do. And when I say computers, I mean the hardware part, the processor that's sitting down in there, not all the incredible layers of software that people have built that sit on top of that. Because computers at the basic can't do very much. What can they do? Anybody want to guess? Yes? Math, absolutely. Mr. Orshevsky? Yes. Is your brother an alumni of this program? Yes. I wish I were a drill sergeant. I would yell at you and promise you all sorts of exciting things. So computers can do math. That's it. All they can do is math. How many of y'all believe me that's all they can do? How many of you think that's insane given all the range of things that you see the computer produce on the screen? Math. That's it. All they can do is math. And when we talk about math, I'm not talking about fancy math like algebra and calculus. I'm talking about arithmetic, adding, subtracting, things like that. All right? Arithmetic. All the computer can do is arithmetic. And they can store lots of numbers. They can't just add them. They can also remember lots of numbers, huge amounts of numbers, gargantuan amounts of numbers. Computers are actually really quite stupid. Everybody repeat after me. Computers are stupid. They are. They're really stupid. I agree with you. Thank you for saying that. Computers are actually really stupid. But how can they do all that cool stuff that we know and love if they're stupid and can only do math? How? Pardon? Some, yes. Everybody in this room is smart. Yes, probably. How can they do that? Computers are stupid, but they are stupid very, very fast. In fact, it's difficult for me to explain how very, very fast they are stupid. Computers are stupid. They are stupid incredibly fast. They can't do much, but they can do it really, really fast. Okay? In fact, they can do it so fast that it is difficult for us to understand how fast computers actually are. I mean, they're so fast that it's even hard to explain. But let's give it a shot and see what we come up with. Here's what we're going to do. We're going to have a little competition. Okay? We are going to add numbers as humans, and we are going to race the computer. Does that make sense? So here are the rules. I want you, go ahead and put the computers away if you want, close them up, they'll wake up later. Get out a piece of paper, get out a pencil, and we're going to add some numbers. We're going to have a little race. And The fastest person in the class is going to be the human champion. So everybody try and add these numbers up, and whoever wins is the fastest, okay? And we'll use you as our champion. And I'm going to get out my stopwatch here to time it. All right, so here's what you can do. Pen, pencil, anything mechanical you want if you have your abacus with you. A slide rule if you ever use slide rule. If you need a slide rule, you can use log tables, which are probably computed on a computer, but we'll do that anyway. Here's what you may not use. Anything electronic that has a battery or a power source, other than your brain, which is partially electronic. Okay? And what we're going to do is I'm going to flash some numbers up, and we're going to add them together as fast as we can, and we'll time and see how long we are. Everybody ready? Are you sure? All right, on our mark, get set, go. Raise your hand when you're done. Okay, 19.48 seconds. Yes, ma'am. You want to read out your number for us, the answer? Bravo. A round of applause. That's actually the class record. That's the fastest anybody's ever done it. Round of applause, please. 19.48 seconds. Very good. Okay, so we were able to add these large numbers. At least one of us was able to add these large. You can get your computers out again if you want. So we were able to add these very large numbers together in 19.48 seconds. Is that fast? Is that fast? How many of y'all think 19.48 seconds is fast? How many of y'all think it's slow? Computers laugh at you, okay? And let me just show you how much they laugh at you. I created this spreadsheet here so that we could do a little calculation of how fast we are compared to the computer. Well, that's too much, isn't it? This Zoom thing is crazy anyway. All right, so here's what we have. We added two numbers in 19.48 seconds. A computer adds 2.7 billion numbers a second. So the computer takes on the order of 3 to the minus 10th seconds to add two numbers together, which means in the time that we took to add two numbers, the computer added 52.5 billion numbers together. 52.5 billion numbers together. How many people are there in the world? 6, 7 billion? 7 billion. So if everybody in the world, every human being in the world could add as fast as our class champion, and then we assign them all numbers, and we had everybody add up numbers, one computer chip by itself would still be on the order of what? 6 or 7 times faster than all the humans in the world put together. One single computer chip. Is that amazing? Remember I said computers are the most amazing tool ever? This is insane. It is insanely amazing. And in fact, if we wanted to see how long it would take one of us, if you did nothing for your entire life, every day, it would take you 1,667 years, rounded, to add up as many numbers as a computer would in a second. If you stopped to eat and sleep, it would take you about 5,000 years. This is most of humans' recorded history. Are you impressed yet? Are you not amazed and amused? This is incredible. There is no other tool we have, none, that provides us the same scale of efficiency as a computer. There is no shovel that will let you dig 52 billion times as fast. There is no car that will let you go 52 billion times as fast. When I say computers are amazing tools, this is why. They are dumb, but they are dumb so incredibly fast that we cannot even comprehend it. 1 second of computer work would take you 63 entire lifetimes, and you would be bored the entire time. Okay? So computers are absolutely incredible. Now, jaded students, it's incredible. Okay, let's give it another comparison, okay? By comparison, if a computer could help you run faster, the fastest run in the world can run 100 meters in 9.58 seconds. If there was a computer or a tool or device that could help a runner run as fast as a computer can help you think and add numbers, then the human runner would run about 8.1 million kilometers in the same time, which is, I think, 2,820 times the speed of light. That's how much faster a computer is than your mind for adding numbers. All right, so it's a bad analogy. We can't even understand what it means to write. And then last semester I did this whole analogy about, if computers generated P, then they would fill up the Potomac River 4 times a day. But that didn't go over very well, so I'm not going to do that this year. But the thing that we have difficulty imagining is the scale of difference between what a computer can do in terms of adding numbers and you can do is just incredible. All right? So computers are dumb, but they are dumb so incredibly fast that they let us do things with it. Right? Seriously, computers are stupid, but we have so much stupidity at our hands that we can just do incredible things with it. Right? We have more power than we can fathom. The computers just sitting in this room are probably more powerful than all the computers in the world 20 years ago, maybe 30, something like that. Right? Because they just keep getting faster and faster and faster. Okay. I've been talking, or ranting as I like to call it, for about 25 minutes. I like to give you all a little break every once in a while because I know I can talk a lot longer than you can listen. So we're going to take a minute and 30-second stretch break. Feel free to stand up, jump up and down, stretch, clap your hands, make noise, talk to your neighbor, flee the room if you want to take this opportunity to do so. All right. Was that a nice little break? Let me just encourage something. Sometimes I, get insane and I go off on a tear and I talk and all of a sudden like an hour and a half has gone by. And I try really hard to look at you all and pay attention to your body language when you're yawning and like getting progressively more slumped in your seats. If ever I'm going on for like 20 or 25 minutes and you're like, God, I just can't take this anymore, I need a break, just raise your hand and just point at the clock and let me know that I've been going on too long. Like I said, I can talk a lot longer than you can pay attention. Just ask my children, right? They tune out in like 3 seconds. So anyway, so welcome back. Let's look at what we can do with this vast reservoir of computer stupidity we have. All right. So we can start something running, right? We can say to the computer, hey, here's a program, start running it. We all agree computers can probably do that. We can tell it to start running an algorithm. By algorithm, we actually mean program, because program is just an algorithm. A program is an algorithm that does two things. Stupid thing. It interrupts you? Okay. An algorithm that the computer can execute and people can understand. So we can start running a program. We can stop running a program. We can say, that is enough, please stop. God, the other thing about having like 45 people in the small room, it's going to be so warm. Isn't it? Everybody's going to be groggy. I'm going to have to get, water balloons or something. So, all right. We can stop running a program. We can read input. That is, the computer can take time out of all its very fast things to ask something of you, the very slow person. Input is particularly useful if you want your program to be at all interesting, right? Any program that doesn't take input just always does the same thing when it's run, which is dull. And we don't want to do dull things. We want to do fun things. We can show output. This is useful to us because the program is a tool for our mind, and we want the computer to do thinking and remembering for us, but then to remind us through somehow. So output, most of the output in this class will be on the screen instead of talking. And then we're going to perform operations. And by operations here, I really mean math operations. And we're going to talk quite a bit about the number of operations we can do, but when you see operations, you should think some sort of math. Every operation we perform is going to refer to a piece of the computer's memory. We'll see this later, but the computer has like boxes in memory where it remembers things, and every operation is going to refer to something the computer has in its memory. The computer is just a giant machine that has a giant hopper of information that feeds into a processor that grinds that information and puts it back into the hopper. That's it. We can make comparisons. This is useful, so if we have two numbers, it'll tell us if one number is bigger than the other or not. And we use this quite a lot to determine in our program which way we want to go. Because we might say, do you want to quit? Do you want to do math? Do you want to do multiplication? And you're able to make choices based on these comparisons. And that's about it. Literally, that is about it. In the hardware of the computer, that is about all you can do. So, programmers are lazy though. And nobody wants to walk up to a computer that can only do these boring things, adding, comparing, and stuff like that. And programmers are lazy, and when I say lazy, I mean lazy in a good way. I mean lazy in terms of getting the most amount of work out of the least amount of effort possible. How many of y'all like that idea? Maximal efficiency. Yeah, me too. I get into arguments with my wife about it because she's like, can you go get the trash can out of the driveway? And I'm like, well, I'm going to be going down to get the mail in like an hour. I'll just get it there. And she's like, dude, it's like 20 feet away. You just parked the car. Anyway, so I'm lazy in the way that I like to optimize things, and I encourage you to be lazy as well. All right? And when I say lazy, that means don't do work you don't have to. So programmers are lazy in the way that they don't like to do things they don't have to, and they particularly don't like writing code over again that they don't have to. So what ends up happening is when people are coding, they try and write their way in a code that can be reused. And they try and write code that other people can use so they don't have to solve the same problems over and over again. And this, besides being something we'll use in this class, is what makes your computers so amazing. Is that you don't have to sit down and write stuff from scratch every single time. You're reusing code that other people have written. That is where all the power of the computer comes from, is the combination of all these different algorithms running on the computer quickly and working in concert. Okay? So, programmers write a lot of stuff, and we're going to be taking advantage as part of the C++ language that we're learning of a lot of things that are already written for us. We'll also be writing stuff, but we will be taking advantage of it as well. So we'll be able to think of these as like sub-algorithms you can use. So later, when we're thinking about algorithms, instead of just thinking about like one series of step-by-step, we'll take the problem and we'll break it down into smaller pieces. And for each piece, we'll have a separate algorithm, and then we'll combine all those pieces back together. And at the end, we will build giant killer robots with chainsaws for hands. Well, maybe not that part, but at the end, we'll have a much more powerful computer than we might have otherwise. Okay. Now, one of the things about this class is that we're going to be able to create our own sub-algorithms. I mentioned this. This is going to be project 3. We have some other stuff to learn about that before we create our own sub-algorithms. All right. So, how can we think about what the computer does in terms of an algorithm? The computer can start a program, it can stop a program, and it can do stuff in between, right? Do you all agree that before starting the algorithm, the computer's not doing anything? Do you agree that after stopping, it's not doing anything? So those have to be our bookends. We start, we stop, we do stuff in between. Everything that we do in between is going to be step by step. Step by step. The computer is just a blind calculating machine. It does everything step by step. So how can we think about this? Well, the way that it was done back in the day, when computers were large and filled this room and generated more heat than even you do, was people were not able to just sit at the keyboard and bang and do things because the computer time was too slow and too expensive, so they had something called punch cards. Anybody ever heard of punch cards? You have these cards, you write out your algorithm, you punch them in there, you bring the cards to the big hopper, it sits on a bunch of shelves until it was your turn for your cards to be run through the computer. Somebody like the high priest of the computer would put these in, it would go through, you'd have some output, they'd put it in your cubby, you'd come back the next day and you'd get the output. And then you'd find out that you made a mistake and you'd have to do it all over again. So what they did to avoid the part where they had to do it all over again for making a mistake is they drew what's called a flowchart. And a flow chart, it's hard to draw on the board in this room at the same time I have the screen down, but the flow chart essentially is going to be, you have a line with boxes, and you literally are able to follow the boxes through every single way to figure out what the flow of the program is until you're done. And you can only ever go along one branch at a time. And I'll show you some more picture of this, but a flow chart is, you start at the start, you stop at the stop, and in between you are always following one single line through to figure out where the flow goes. So let's take a look at what those look like. For starting, we use this oval that says start. Anybody have any idea what this does? Any guesses? Yes, it starts. And what we do from there is we attach a line to that. We find the start button, we attach a line, right? And you just follow the arrow. We do some input. In flowcharting for computers, input and output are both represented by parallelogram. Is that what that is? Parallelogram. Trapezoid? Triangle? Is that a circle? Quadrigon? Somebody help me out here. Geometry majors. Parallelogram, okay, great. Rhombus. Somebody say rhombus? Is it? Are you a math major? Okay, good. No, you stay near the front to help me out. I'm happy with that. So, okay, so we have a parallelogram. We have a parallelogram, and parallelogram is going to be used to represent input and output. So this algorithm, and this right here is an algorithm. It's not a complete one, but it's an algorithm. It has 2 steps. Start, do some input. Is this a very exciting algorithm? Not yet. Just wait. Okay. After we start and do input, we can do some operation. So we start, follow line input, follow line operation. Every program that you ever write will have what's called the flow of control. And the flow of control is where this arrow takes you, the series of steps that this takes you through. This is the graphical way to represent this. We do some operation, and then from there, we can do a decision. A decision is indicated by a diamond. A decision will always have 2 branches, one for yes, one for no. Every decision you make will have to be either true or false. Oh, by the way, that's a lie, okay? And let me just step aside and tell you about the fact that I am a chronic liar for a moment. I'm going to lie to you in this class. I'm going to lie to you a lot. I'm going to lie to you often. I'm going to lie to you joyfully. There's a lot of ways that I'm going to lie to you. There's one way that I'm not going to lie to you. I'm not going to lie to you in a way that I expect you to know the truth. The reason I'm going to lie to you is to simplify things that are very complex. If I tried to go into too much detail about everything, it would be bad. We would have a bad day. Okay? So I'm going to lie to you to hide complexity of things sometimes, and then later I will reveal the truth behind my lie. Are you okay with that? All right. So right now the lie is that every decision has to be true or false. Are you all happy with that lie? So every decision has to be true or false. When your algorithm runs, you are always going to be following one of these lines. You'll start, do some input, do some operation, go to a decision. You will either go to the yes line or you will go to the no line. You will not ever be able to go to both. Once the decision is made, it is final and you go on from there. Finally, we do some output. Along either branch, we choose to do some output, and then we stop. So this is the visual representation of a very simple algorithm. This is an algorithm. We start, take some input, do an operation. Based on the results of that operation, we make a decision, and then we output something, and then stop. Let's actually give this a more concrete idea behind it. Let's say we want to write a program that will allow the computer to tell us whether a number is even or odd. Does that sound like a particularly complex algorithm? How long do you think it will take the computer to execute an algorithm like this? The time is measured in nanoseconds, except for the time it spends waiting for you to do input, which is measured in eternity from the computer's point of view. But we start, you input a number, somebody shout out an integer. Okay, we're choosing the integer 17. So 17 gets put in there. We do some operation on there. What operation, what mathematical operation can we do to a number to determine if it is even or odd? Yes? We will divide it by 2, and based on that, what will we know? How will we know if it's odd or even based on dividing it by 2? Exactly. So if there is a remainder, it is odd. But you're absolutely correct. If it's an integer, an even result, then it's even. If it has a remainder, it's odd. So then we decide, what decision would we make up here? Whether there was a remainder or not. And if there was a remainder, we would print out, and this output would be what? Yep. Yes, if there was a remainder and we followed the yes branch, you would say it was odd. If there was not a remainder and we followed the no branch, you would say it was even. And then the program would stop. Okay. Does this seem tedious and slightly simplified and boring to you? How many of y'all say yes? I get it. Please move the hell on. Okay, I don't care. It's important. We're going to go over it in detail. I told you, remember that chart. Things are a little easy and they ramp up at the end. This is important stuff. You have to understand every single program we're going to start, we're going to stop, and there's going to be a series of steps that we follow through to the end, and we're only ever going to follow one branch of any decision at a time. Every program we run, we'll be able to literally trace the flow from start to finish. All right? And I will tell you, this is a useful skill to have. I've been doing this for a while and reading code. I do some consulting on the side from time to time, and companies pay me. They sit me down in a room with a giant pile of source code, and they say, given this program, tell me what the algorithm is. And I literally find where to start, and I start reading code, and I keep track of what's doing them until I get to the end. Okay? And this is all for patent stuff, because a patent is an algorithm, and they're always interested in knowing whether the code, the algorithm that's expressed by the code matches the patent. They pay me way too much money to do that. So it's I don't even know why I said all that, but I did. Okay, so there we have it. All right, here's a question. What if you do something often in your algorithm? Let's say that instead of wanting to just look at one number and determine whether it was even odd, we knew that somebody was going to give us a file, and that file contained the NSA's collection of everybody's social security number in the United States. How many different social security numbers does the NSA have? How many? Like 300 or 400 million, right? So how many of y'all would want to write this little algorithm over and over again 300 or 400 million times? Nobody would, right? So what we're going to do instead is, if there's something we're going to do in our algorithm, instead of copying it over and over like 300 or 400 million times, like I was implying, what we're going to do is we're going to design that one piece as a sub-algorithm. And so here's essentially what we're going to do. We had start here and stop here. We can take any piece of the algorithm, and using this box right up here, the one that says sub-algorithm, it's like a rectangle with lines on the outside. That is an operation. That means an operation that you defined, a sub-algorithm that you defined. And you're able to package all those steps into one little box. Okay, you all kind of see what's happening there? Right? Instead of having to write out these steps every single time, we say, hey, every time you see this box called sub-algorithm, know it contains this set of steps inside. Our sub-algorithm we're talking about is how to tell if a number is even or odd. So we might give this sub-algorithm a name, which would be called something like figure out if this number is even or odd. So that's pretty long. We'd be too lazy to type that because we want to be efficient, so we'd come up with something else. But there we go. Everybody good? By the way, I normally bring candy to class, which I throw at people to encourage to ask questions and speak, but I ate it all, and we haven't been to Costco yet, so we'll get more. Feel free to interrupt me. I know I'm like raving and ranting today with my little mic on and slides and stuff. Most of the classes will not be like this. This is like, there'll be one more class where I do lecture stuff, and then it's going to be me typing code like a Shakespeare monkey or something up here on the front. All right. So, any questions so far? And remember, I know about the 17-second rule. You do not need to wait 17 seconds. Yes?
Would that still be doing the sub-algorithm one after another, or would it be doing multiple at the same time?
Okay, so the question is, would it be doing them one after another, like you do the sub-algorithm and then do it again, or would it be doing multiple sub-algorithms at the same time? You have hit upon the giant change that is happening in computer science today. Perhaps wittingly, perhaps not. most of the time when our program's done, they will be doing each sub-algorithm one after the other, serially, okay? Today, however, the big trend in computer science and computers is instead of having one processor, we have like 4, you have Macs, you probably have 4 or 8 processors on there, or you have thousands, because the video cards in your computers these days are also tiny computers and they have hundreds or thousands of small processors on them. So today, the trend in computer science and algorithm is to do all of these things in parallel as much as possible because it's faster. It's also more complicated. So while parallelism exists, while it is possible sometime to run different sub-algorithms at the same time, we will not be doing it in this class. You'll be doing it later. So does that answer your question? Thank you for asking. Other questions, please. Random questions. Yeah. Great.
Sorry, I should have asked in the first day of class. It's about the book.
Uh-huh.
Do we need a print copy of that, or can it be a digital copy?
So the question was, do you need a print copy of the book or can it be a digital copy?
Both were on sale in the bookstore.
You are welcome to use whatever suits you. I'm not going to require you physically bring the book to class and look at things in the pages. Let me just say a word about the book. The book is actually, by computer science textbook standards, terse, because most books are like this thick and have like 8 billion pages of examples. That book is terse, so I'm actually going to expect you to read it. Like, I feel bad about assigning a chapter that's got like 800 pages of stuff. But this book is terse, since I will give you readings to do before class. I won't expect you to have the book in class. So does that answer your question? Yeah. Other questions? Oh, by the way, the book itself is a print book. It's got like 11 or 12 chapters, and then there's like 4 chapters that are web only that you will download that will be digital. I downloaded them and have copies if you have difficulty finding, like anybody can download them. So, but that's for later in the semester. Other questions? No? Nothing? All right. So feel free to interrupt me while I'm ranting up here. All right. Everybody good with this idea of flow, that the program is only going to follow like one little thread of control along? Everybody good with that? Everybody is familiar and happy with this idea that we will only do everything one step at a time? Everybody happy with that? These things are important. You have to understand that. Okay, so if we were going to redo our algorithm with our sub-algorithm, we would start, do our sub-algorithm, and stop. We would not have all those other boxes inside, because we would know that if we needed to know what was in this sub-algorithm, we could go back and take a look at it. All right, does that make sense? All right, so the question is, now that I've shown you how to use flowcharts, how are we going to use them in class? And the answer is, we won't ever use flowcharts in class. The reason I want to show them to you now is because I want you to have in your visual memory this idea that we are going to always be going along one particular path, okay? One particular path. Everybody comfortable with that? How many of y'all think you get it and I can just go on and do something else? How many of y'all get it? How many of you don't get it? How many of y'all didn't have hand injuries today? You're looking better. Congratulations. All right, so we're not going to use flowcharts. I have used them in the past. They're just unwieldy and they're difficult to use. But they are very useful to have this idea that the program has flow. It starts somewhere, it stops somewhere, and in between, it's only ever doing one thing. Okay. Now, when we talk about algorithms being a series of ordered steps, flowcharts make this series of steps quite explicit because you're doing like choose your own adventure along the line, right? And just doing different stuff as you go along. And the flowchart makes this order expression. So how else can we represent algorithms? And this question is important for 2 reasons. First of all is that you have to be able to figure out what your algorithms look like before you turn them in. And second is that there's a homework about algorithms due on Thursday where you have to do this. So I don't know which reason's more important to you. The first one's more important to me, but it's good for you to have some practice. So how else can we represent this? Well, one way that you might be familiar with is to do an outline. How many of you ever outlined papers? How many of you ever outline paper when you're actually writing papers these days? Like, I know, really? All right. Most people just sit down and start writing these days, right? And cut and paste things around. Here's what we're going to do. We're going to have specific language for the possible operations of our outline. And these things match. These things match exactly what we saw on the flowchart. We're going to have start. We're going to have stop. We'll have some input, output. We'll have some calculate, and we'll have a decide. And decide means you do one thing or you do the other thing, but not both. For calculate, this is just tell us what you're calculating. It can be a math operation, a math equation, something like that. So here is exactly the same thing we just talked about, which was an algorithm that takes some input, determines whether or not the number input is even or odd, and then outputs it, written in the same way. And let's all practice. Where do we start with this program if we wanted to follow this? We start at start, and we go, okay, start. Now, in this representation, after you have done a particular line of the algorithm, you go on to the next step, which is the one below it. What is immediately below start? Input. So input, we say, tell me a number. What number are we inputting? 17. 17 seems to make us happy, so we're going to 17. We do a calculate, divide number by 2. So the operation we do is we have this thing, a number, and now we're dividing it by 2. 17 divided by 2 is 8.5, or 8 with a remainder of 1, right? Is that right? Yeah, 8. You sure? Yeah, 8, okay, 8. With a remainder of 1. So now we decide, is the remainder 1? How many of y'all think it is? It is. So we go, okay, if so, we do this. If not, we do that. So we go to the if so line, we say output odd. If not, we skip, and we go to the next line, stop. So we're just going down step by step along this outline. Does this make sense? You all see how this works? The flow in this is essentially top to bottom. So we start, do stuff. However, we have these ifs that allow us to skip stuff that is not relevant. But other than that, it's the same as the flowchart. It is another way of representing an algorithm. Everybody good with that? All right, this is what you're going to use on your homework. For your homework, which is due on Thursday, you have a set of problems to solve. And the problem is it's late and you're hungry and you want to order a pizza and you have 2 choices and you have to decide which pizza is the better value. You're optimizing your pizza selection. So you're going to write your algorithm exactly like that. You're going to input some numbers. The numbers are going to be the sizes of the pizza. You're going to do some calculations, output which one is the better buy, using this language we saw there. You're also going to use this on the design on the first couple of projects, because I'm going to have you turn in design documents, which is your algorithm for the program that you're going to build, with the idea that if we make you think about your algorithm before you write your program, then you will end up thinking about your algorithm before writing your program, which is beneficial to you. Okay, so we've talked a lot about algorithms. Let's talk about programs. Have I told you what we're going to use for programs yet? We're going to use a language called C++. The language name is C++. Let me tell you, C++ is one of many computer languages that will allow us to represent an algorithm in the way a computer can understand. Anybody use C++ before? So Java, the few people who use Java, is descended from C++. So some of it will look familiar to you. Now, what's going to happen is we are going to write our algorithm, once we learn this language, in C++, which is a language that we can use to read to things, to understand it. The computer itself does not understand C++. It does not. The computer speaks a special binary language that is nothing but lots of ones and zeros. In the early days of computers, when people programmed computers, they programmed in a bunch of ones and zeros, literally by flipping a whole bunch of switches, which I'm glad we don't do anymore. So C++ is language, and we're going to see, just like how we talked about algorithms of flowchart, algorithms as an outline, we're also going to see how C++ allows us to develop algorithms in a language. Now the thing about it is the computer doesn't speak C++ directly. What the computer speaks is this weird binary language that's often called machine code. And the way that we get our C++ that we write into machine code that the computer can understand and execute is by using a special program called a compiler. I don't think anybody here, if you haven't programmed before, has done anything that's quite like a compiler, right? You write a paper and you're done. The closest thing I can think is if you were like trying to write a paper for your Czech language class. How many of y'all are studying Czech? You want to just learn Czech? Anybody speak Czech? No? Okay, well, you have to write a paper in Czech, so what do? You write your paper in English, you feed it into Google Translate, right? And it outputs some Czech for you. And you trust that it works. Okay, the compiler is essentially the translator that's translating C++ into the binary language of computers. Right. That's what it does. So, how y'all doing? Do you want a 1 minute break? It's really, yes, no? All right, I'm going to keep talking then. You have to learn to shout at me if you want to stop, okay? Let's look at the algorithm. We're going to do this. The first step in our process of developing algorithms in C++, the very first step is what? Start early. I told you that last class. The first step is going to be start early. You need to start your projects early, okay? The next step is you are going to read the problem that I gave you. This class, how many of y'all like word problems in math? Do you remember math? Like when you're in school, they'd give you some stuff to add, and you'd be like, yeah, awesome. And they give you word problems, and you'd be like, how do I figure out which number to add from this? Well, I'm giving you giant word problems. And what you're going to have to do is read the problem, and from that, extract the algorithm. Once you have designed your algorithm that solves the problem, then, and only then, you will start writing C++ code. Now, when you write your code in C++, what program are you going to not use for this? Not use. Do not use Word. Do not use WordPad. That path lies madness, okay? Do not use it. We will help you, and I'll give you some particular editors that are kind of bare bones text editors that you will use. If you use Word or WordPad, they insert invisible formatting marks in there that you cannot see, but when the compiler tries to read your code, the compiler sees it, and it will spew out errors, and they will be invisible to you. It's like invisible mistakes get inserted in there. Okay. All right. Once we have edited the C code, we will use the compiler. And we will take this C code that we have written, the C++ code, and we will compile it. Now, the compiler is a piece of software that is very picky about syntax. Like the way you write your syntax is going to matter a lot to the compiler. And when you make a mistake, it will yell at you. And here's what's going to happen, is you're going to look and say, when I compiled, did I get errors? And you know what the answer is going to be? Yes. Almost always the answer is going to be yes. And what's going to happen is you're going to have to look at the error message from the compiler, which I can assure you, you will find not at all clear. And we'll talk more about debugging as we go on. But you will look at the error and go back and edit your C code again to try and fix the error. Okay? You will compile again, and after some passes through this cycle, you will eventually reach a point where you have taken out all of the syntax errors. That is, your program will compile correctly. At which point, now you have to run some tests. Let me make an important point for you. Just because your program compiles correctly does not mean your program is correct. Okay? Let me give you an example. English has a syntax, doesn't it? And if you're typing something in Microsoft Word will put a little, what, is it green or red underline where you make syntax errors, right? I can give you a word, I can give you a sentence in English that is syntactically correct, but makes no sense. The semantics are bad, right? And we could just do this Mad Lib style. Somebody give me an adjective. Fast. Somebody give me a verb. Oh, okay. Somebody give me a noun, and don't say rabbit, greyhound, something like that. Anyway, that's a failed experiment. Okay, but I mean, you can come up with a sentence that makes no sense, right? Like it's hard to do because I always make sense. But something like, you know, the fast toaster ran yellow, right? Syntactically correct, but it doesn't make any sense. That was a bad example. Anyway, so you have to run tests to make sure that even though the semantics are right and the compiler's working, your algorithm is correct. And if it's not, then you have to essentially go back to this point and say, hey, my program ran it compiled, but it's doing something wrong. I need to go back and think about my algorithm to see where I went wrong on this. Okay, and then you go through this again. You change your algorithm, you edit the C++ code, you've introduced some errors, you go through here, eventually you go back up, run the test, and eventually your output is correct. Okay? At that point, you will submit the code. Through this class, we will be using Blackboard, and you'll be uploading your code through the web form on Blackboard, and then you will stop, and you are all done with your project. Ideally, this stop point will be some period of time in between. Now, the reason we're starting early is because here, this cycle right here, and this cycle right here where you're running tests can be confusing. This is, remember I said on the first day when you're writing code, you're going to get stuck on some stuff? You're going to get stuck here because you're going to get some weird errors and you're going to occasionally get stuck on this algorithm thing where your algorithm is not correct and you won't see why. And in this class, we have 10 TAs, which is one for every about 10 students. And so there will be somebody around almost all the time for you to get help from. And you can also, later you'll be able to email me your code and I'll take a look and be able to fix things too. Mostly what happens is the TAs try and fix your problem, and occasionally you'll have something that's so weird and subtle that they'll kind of kick it up to me and I'll look at it and try and figure out what's going wrong. Okay? But this right here, this error thing and this algorithm correctness thing is where you need to get help, which is why you start early. All right. Questions on this? This is how you're going to build your code and compile it. And this week, we're going to have a homework about algorithms, so you have a practice doing algorithm design. Next week, we're going to give you a very simple program just to type in that you don't have to design the algorithm for. We'll give you the code, and your job will be to do this process where you type it and submit it, just to make sure that you're familiar with the tools. And then we'll actually get into the code writing. All right, questions so far? All right, two things. The first is that I think a lot of you are really going to like programming and writing code. It's like solving a giant puzzle, right? You have this algorithm, you have this problem you're trying to solve, and you're trying to use the computer to solve it. And what's going to happen is you're going to develop things, you're going to see it go wrong, and you'll be like, I did it wrong, and you're going to learn from your mistake and fix it. And when you're done, particularly later in the semester with some of the bigger projects, you're going to be like, yeah, right? You're going to be like, I did that. That was really awesome. So programming can be really fun. It can be frustrating because you're going to get bogged down and they're like, what is going on? But when you fix it, it's going to feel really awesome. All right? That part is really fantastic. And I can tell you, I've had bugs that took me like 28 to 30 hours in front of the computer to fix. And I had forgotten one character. I forgot to push the key one place in my program, and it took me like forever to figure out where it was. And when I was done, I was so relieved. It was awesome. And then my program still didn't work, and I had to fix other stuff. But anyway, that was good. Okay. The other thing about the projects in this class is that I try to come up with a different topic every semester. Last semester we did, and it turned out to be awesome, we did a calculator that calculated heart attack risk given physical attributes of people. And it turned out that halfway through the semester, there was a big study where they came out with a new heart attack risk calculator, and we're comparing it against the old one, which is the one we were programming, which is pretty awesome. So that was lucky for me. I haven't actually thought of a theme yet for this semester. I have like a week to do one. I'm considering things like nowadays the rage. Have you all heard of Bitcoin? Anybody mining Bitcoin or have some Bitcoin? Anyway, I was thinking of doing something around like cryptocurrencies like that. That might be fun. It might not. I don't know. And I'm open to other ideas if you have something interesting and interest. So you can talk to me about it. Otherwise, I don't know. I might do something like Jersey Shore related. I don't know. I'm a big One Direction fan, so maybe like a One Direction fan. You all One Direction? Directioners? No? Yeah. All right. So when you're done, you're done. All right. So today, here's what we've talked about. We talked about algorithms. What is an algorithm? Okay. A series of ordered steps used to complete some problem. The one thing that I expect you to know when I run into you on the subway someday. We talked about how to represent them a couple of different ways. We talked about outline, and we talked about flowcharts. We talked about the algorithm that we use for programming. Start early, read the problem well, design your algorithm, edit the code, compile the code, make it work. After it works, you test it until your testing's complete, turn it in, and you're done. And we'll practice that. There is nothing left for us to get into except C++. And in order to understand C++, we have to understand how computers work in excruciatingly deep detail. Okay, that part's a lie. We just have to know a little bit about how computers work. So, because it relates to the language. All right. Now, that is all for now, for lecture, for me jabbering at you. But we're not leaving. I'm going to turn on the lights, shield your eyes. It's going to be bright. Okay. So here's what we do in my class often, is that we will stop and we will do problem sets in class, and we'll do some practice. But the way we do it is we don't just sit here in silence. The way we do it is through what's called a partner-assisted exercise. So I'm going to hand out this sheet. I would like you to turn and introduce yourself to one of your neighbors, perhaps all of them. Shake hands, say your name. I'll hand these out. So we'll pass these around. All right, everybody have one? Anybody not have one yet? Can you pass them towards the middle if there aren't? There should be extras somewhere. Here, I'll take them. Thank you. Anybody else? All right, so here's what we do. We're going to do this problem-solving exercise. And the problem-solving, I'm sorry, I didn't mean to neglect you. The problem-solving exercise is this. One person will be listening and giving feedback, and one person will be thinking out loud as part of the problem. Your job as the problem solver is you read the problem out loud, and then you start talking. You say, well, I think it might be this. Let's talk about that. Do the other thing. Maybe it'll work this way. Maybe it won't. Your job as the listener is not to go, that's dumb. You're never going to do that. Your job as a listener to go, are you sure about that? How about this? What about this other thing? It's just to give neutral feedback and listen as they do the problem. This is an amazingly powerful process. I as a professor, seem like I'm a genius because students walk into my office and they go, I have this problem. And I go, well, what's your problem? And they start explaining the problem. And the fact that they're talking about it out loud makes them think about the problem. And they'll go, I have this problem and I noticed that and I didn't do that here. And oh, here's the thing that's wrong and I fixed it. And then they go, thanks. And I go, you're welcome. And I look very smart and I haven't said a word. Okay? Just because of the way our brains work, if you talk about your problem, it forces you to think about it. So, you have your partner with you, and we're going to do some problems next. There are two. There's one called a new solar system. There's one called a watery mess. Let's do the solar system one first. No giving away answers. And then the other one next. One of you be the solver, one of you the listener. We'll have like 5 minutes, and then we'll do the other problem. Okay?